Hi, everyone. It's really great to be here. I've noticed that you've been a really great audience, asking really interesting questions. So my work mainly focuses on the Intertropical Convergence Zone. As the title suggests, I look at the dynamical constraints that the flow imposes on the location of the Intertropical Convergence Zone. So I thought I would use this lecture as an opportunity to kind of talk about how people have looked at this in the past, like what are the different models that people have come up with, and also talk a little bit about my own work, which makes use of kilometer scale icon simulations. Okay, I'm sure I won't be the last person to show you this in this workshop, but this is the precipitation climatology, annual mean precipitation climatology that you get from iMerge. And the Intertropical Convergence Zone kind of sticks out as this narrow region of yellows and reds in this image. What is remarkable is the amount of precipitation that falls in this narrow region. So I don't know if the legend is, if you can read it, but the yellow starts at 3,000 millimeters per year. So it's quite a lot of rainfall falling into this narrow region. And I mainly look at precipitation in the ocean basins. So that's what I'm going to focus on. So the ocean basin that I want you to focus on right now is the Pacific. And if you look at the Pacific basin, you see that there's an asymmetry in the distribution of precipitation. And this has come up, I think, when Vidyut was talking about precipitation as well as one of the questions. And if you take the zonal mean of the precipitation, you'd see that the maximum in precipitation is kind of located in the northern hemisphere. And this has also stirred a lot of debate and questions on why the ITCZ is dominant in the northern hemisphere. There are some answers, but it's still an open question. And there's, I think I mentioned all of the points. In the previous picture, the asymmetry was only visible in the Pacific basin. But if I look at a specific month, which is April, you can also see it in the Atlantic basin. So you have more broad structure in the west versus the east. So I thought, because I'm also an in-person speaker, we could make this a little bit more interactive. So the question that I have for you is, if you were to think back to your tropical meteorology courses, what would you define are the characteristics of the Intertropical Convergence Zone? So I'd start off by giving the easiest answer possible. So you would say that, okay, tropical precipitation is typically located over the highest SSTs. Are there other features, like in terms of winds or in terms of pressure or something else that you can think of that you want to tell me? Yeah, strong vertical motion, yes. Strong convergence, yes. Yeah, high moisture. But can we think of the dynamical variables as well? Like Vishal said, low-level convergence. And the low-level convergence kind of comes from the trade winds meeting, right? So the meeting point of the trades, the term for it is the confluence, axis of confluence. It's also located in an old term for it, probably is the equatorial trough. So these are the different things that would come up if you look up in a textbook on tropical meteorology. So when I read this, I thought, wow, that's a remarkable feature for all of these to come together. So do you think all of these are co-located? Like, let's say the precipitation maximum, is it always co-located with the highest SSTs? Or is the precipitation maximum exactly where the trade winds meet? What do you think? Are they, when I say are these features co-located, I want you to think of an local extrema, is the maximum precipitation co-located with maximum SST or minimum sea level pressure or high cloudiness? Yeah, exactly. So if you were to plot the zonal mean and think of a single basin, or even eastern basin versus western basin, you think they would all be co-located? Yeah, okay. This question was asked 50 years ago, and they say at that time, I think, there were like high resolution observations available 50 years ago, and they kind of looked at all of the local extrema in these features that we talked about, and they plotted the meridional migration as a function of the seasonal cycle. So the x-axis here is time, different months of the year, and y-axis is latitude. So there's a lot going on, but just from looking at it, glancing the large features of it, you see that they're not co-located. And this is, I should mention that I'm looking at Eastern Pacific because we saw that there's east-west asymmetry, so it doesn't make sense to take the zonal average across the whole basin. So they've focused on, this work focused on Eastern Ocean basins. And yeah, so they're not all co-located for most times of the year. And the solid lines, so I've indicated sea surface temperature by red because it's hot, and precipitation by blue because it's water. And the meeting point of the trades is given in black, the solid line. And you'd see that in the Eastern Ocean basins, this picture of the trade winds coming and there being high SSTs and leading to precipitation kind of breaks down. And you see that during boreal summer, these months, there's the highest separation between SST maximum and the precipitation maximum. And the precipitation maximum is kind of located to the south of the confluence axis. So it's located in the southerly trade wind regime. In the Eastern Ocean basins, especially East Pacific, there's cross-equatorial southerly flow, which exists for all times of the year because you see that the confluence axis is always north of the equator. And the precipitation maximum is located in this cross-equatorial flow. And the link that I always try to make in this talk is kind of looking at the dynamics of the cross-equatorial flow and why it's special. Okay, now let's look at Western Ocean basins. So this is Western Atlantic, and everything stays the same. So you have the red showing the meridional migration of high sea surface, maximum sea surface temperature, and the blue showing the maximum in precipitation and confluence axis. And you can already see that the picture is different from what we saw in the previous slide. So you see that for most times of the year, the precipitation and the convergence maxima are to the north of this black line, which is the confluence axis. So they exist in the northerly flow. And the only time they kind of go below the confluence or to the south of the confluence axis is during June, July, August. Again, this is cross-equatorial flow where the precipitation maximum is located. So, okay. And then, I mean, this is moist convective dynamics workshop, right? And I'm going to present a very dry dynamical point of view. But I think, like it was pointed out at the beginning of the workshop, it makes sense to look at this problem from like multiple perspectives because tropical precipitation, be it monsoons or the ITCZ, is inherently multi-scale. And I've made use of this image from the recent orchestra overview paper, which is a campaign that happened sampling the ITCZ in the Eastern Atlantic and the Western Atlantic. And they've kind of indicated all of the scales that we've seen throughout the workshop so far in this image. So you have the visible image at the back, and then you have the dotted line showing the precipitation climatology contour. So all of the mean precipitation kind of falls inside this. And you have the mesoscale indicated by the blue circles and the cumulus scale indicated by the magenta circles. So you have cold pools which fall in the cumulus scale, aggregation, convective aggregation, which we heard a lot about yesterday, which falls in the mesoscale. And you have the mesoscale convective systems, which have both cumulus scales and mesoscales kind of interacting. And you also have what is the large-scale convergence. And by large-scale convergence, I mean, what are the forces that exist in the boundary layer that kind of impose a low-level convergence? And that is the focus of my talk. So I want to kind of think about what are the dynamical constraints that the ITCZ has in its position or its width. Okay. So I guess hopefully that contextualizes where what I'm talking about is with respect to what is being talked about in the rest of the workshop. And the other thing I should mention is when I talk about large-scale dynamics, there's also like ITCZ is a region of high mean and high variability. So I'm going to focus on the mean aspect of it. Okay. This part of the talk, I'm going to discuss the different theoretical models that people have looked at the cross-equatorial winds. Again, cross-equatorial flow, because we saw that the cross-equatorial flow somehow seems to attract most of the precipitation in both Eastern and the Western Ocean basins. Okay. Any questions so far, or can I move on? Okay, so this is the most colorful slide I have, I promise. Because I mentioned I want to talk about what drives the low-level convergence, the starting point obviously would be to look at the horizontal winds. So I have the zonal momentum equation and the meridional momentum equation. And the horizontal wind convergence throughout the boundary layer can be understood through these equations. And I've also highlighted the different forces by different colors. So you have advection in blue, Coriolis in green, pressure gradient in red, and friction in magenta. And typically what people have done in the past is study this from linear Ekman balance. So by this, they neglect the effect of nonlinear advection terms and consider the equations. So and you also remove the time, because it's a balance model, you assume steady state and you look at what the steady state winds look like. So the dominant balances are between Coriolis, pressure gradient, and friction in this linear balance models. Okay, so let's take this model and let's try to understand what would happen inside a boundary layer. So let's look from the surface going to the top. And for the sake of simplicity, let's say that the surface winds are very weak compared to what's happening aloft. Then if you think of the three balance terms, so you have Coriolis, you have pressure gradients, and you have friction. Then because the winds are small near the surface, you can say that the Coriolis is probably not so strong. So you have the dominant balance between pressure gradients and friction. And as you keep going up, the contribution due to friction decreases because you are going away from the surface. Then when you're outside of the range where the friction stops exerting its influence, then you have the balance between pressure gradient and Coriolis, which is called the geostrophic balance. And if you like visualize then and try to obtain the winds from how the forces are changing throughout the boundary layer, you would see that the winds would have to turn as they go up. And this is what is known as the Ekman spiral. And that's given here. So the x-axis is the magnitude of the zonal wind with respect to the zonal geostrophic wind that you would have at the top. And the y-axis is the meridional wind with respect to also with respect to the geostrophic zonal wind you would have at the top. And you'd see that as you go from the surface to the top of the boundary layer, you have the turning of the winds. It's a simple enough model, right? And then let's look what would happen in a cross-equatorial flow, because that's the flow that we are interested in understanding. Okay, so obviously people have worked on this in the past. So there's this study which looked at cross-equatorial boundary layers. And they've used the beta plane approximation. And some of you who have signed up for the other project have seen these equations, and I think Harshit already had coded this up, and we saw some solutions. How these equations are different from the Ekman balance, of course, they have the advection term, but they also have written the Coriolis in terms of the beta plane, where they use the small angle approximation. And what they did with these beta plane equations is kind of imposed like a constant pressure gradient. So you have like a cross-equatorial pressure gradient. So I'm going to illustrate the case. They've done many pressure gradients, but I'm going to take the case where they've not considered the zonal pressure gradient and considered the meridional pressure gradient to be a constant. Okay, and then, so they've plotted the boundary layer winds at multiple locations along the latitude. And so you have one at 3 degrees south, so the flow hasn't really crossed the equator. And they've plotted it in terms of the Ekman spiral. So the dotted spiral is the analytical solution, and the solid one is the numerical solution. And you see that at 3 degrees south, the numerical solution agrees reasonably well with the Ekman solution. And at the equator, you really can't test it because Ekman spiral is not defined at the equator. And if you look at 3 degrees north, you see that the Ekman spiral says that the geostrophic wind has to be westerly, but the numerical solution doesn't agree with it. Yeah? Okay. And then they've kind of plotted the evolution of meridional wind. So this is, the top row is basically meridional wind as a function of height at different meridional positions, so different latitudes. So you have one at 4 degrees south where it looks more or less like an Ekman solution. And then as you move towards the equator, it deviates. And then at 9 degrees north, you go back to somewhat of an Ekman solution again. And they've also looked at the force balances in the boundary layer. And what they find is at 3 degrees south, you have, okay, so C stands for Coriolis, F stands for friction, VA stands for vertical advection, and HA stands for horizontal advection. So at 3 degrees south, they see that, yes, horizontal and vertical advection are non-zero, but they're much smaller than Coriolis and friction. And if you go towards the equator, you see that the horizontal advection becomes very, very dominant, and so does vertical advection. And similarly, at 6 degrees north as well, you have the horizontal advection and Coriolis competing with one another. And similarly at 8 degrees north. So in this very idealized experiment, they could already see that in a cross-equatorial flow, the advection terms are important, and you possibly cannot have a linear Ekman balance. Okay, and how, you might be wondering, okay, this is all well and nice, but how is this important to the ITCZ? And that is where I think this sort of streamlines in the vertical meridional plane come into play. And what they observe is that as the flow, as the advective boundary layers turn into the Ekman boundary layers, you have really strong upward motion. And one of the hypotheses that one of the things that they suggest is that it's hard to test this at this point with like a realistic simulation, but there is a possibility that when an advective boundary layer transitions to an Ekman boundary layer, you have upward motion. Yeah, and you also see that the upward motion is happening also in the cross-equatorial flow. And this was also in line with the observations they had about 50 years ago, where they found, like, they had station data, and whenever the station was located to the south of the ITCZ, they found that it doesn't behave like the boundary layer flow doesn't behave like an Ekman solution, whereas if you have a station to the north of the ITCZ, then it behaves like an Ekman solution. Yeah, so already in this idealized study, you can see how cross-equatorial flow and advection play a role. But people have also had remarkable success with using linear Ekman balance models to understand near-surface equatorial winds. So far, when I talked about the different balances, we haven't really talked about what is driving the flow, and any kind of good model would have some kind of physical intuition behind it. So there's two basic types of Ekman balance models, and I would definitely refer you to read the chapter in this book. The title of the chapter is this, where they go into much more details of it. But I'm going to focus more on the Linson and Negam type Ekman balance models. So there are two basic types. So the first is the Linson and Negam type of Ekman balance models, where the pressure gradients are thought to be driven by sea surface temperature gradients. And there's the Gilles type models, where the low-level convergence within the boundary layer is as a result of the latent heating in the middle atmosphere. And of course, these two mechanisms probably happen on different timescales because the sea surface temperatures vary much more slowly compared to the cumulus heating. But yeah, I would definitely recommend to refer to this for a more detailed discussion. So for the next part, I want to focus more on the Linson and Negam type Ekman balance model. And so I think the reasoning for this kind of comes from, if you look at the zonal and meridional gradients in temperature as you go higher and higher up in the atmosphere, you see that they bear a resemblance to the sea surface temperature gradients. And that led them to kind of develop a model which accounts for sea surface temperature gradients to come into the Ekman balance model. Yeah, so I don't know if that is very obvious from these plots. So you see that the large scale features are somewhat replicated as you go higher and higher up in both derivatives. Okay, all right. Then I thought I would also walk you through the model. It seems like a lot of equations, but it's fairly straightforward. So the first thing that they did was they tried to come up with a model for a temperature at any latitude or a height based on the surface temperature. And that's what is given by the first equation. So their first the first step in the model is to kind of express the atmospheric temperature in terms of the surface temperature. So the over bar means zonal average. So they took the zonal average as one of the contributing factors, and they put in a lapse rate, and they took the anomalies, which are a function of both zonal and meridional directions, and there's also a lapse rate for these anomalies. And so this gives the temperature at any level within the boundary layer in the atmosphere. And the second thing that they did was they assumed incompressibility and hydrostatic balance. So density is a function of temperature alone, and they wrote the pressure in terms of the hydrostatic balance. And the last step was basically to substitute this into this and integrate with respect to z, and that gives you the pressure at any vertical height. So they looked at what the pressure that comes out of their simulation, how it compares with the observed pressure, and you see that it does a fairly decent job of capturing the anomalies. And then they used the pressure that came out of their simulation and plugged it in the Ekman balance model and looked at the winds. And you don't have to know much. So this is the anomaly in the zonal wind. This is the meridional wind, and this is low-level convergence. And you could already see in the low-level convergence that there's something really strange happening near the equator. There's very strong values, and typically this is not observed. And they report that the values that they observe are about 10 times of what is observed in reality. And all of these calculations are done by assuming that there's no influence coming in from the atmosphere above, and there's a fixed lid. And to sort of correct this, they hypothesize that, okay, maybe the fixed lid is not a good enough approximation. What if there's low-level convergence happening into like a particular column? Then there should be like something that should relax the pressure gradients there. And that's what they try to do with the correction, which they call the back pressure. So they wrote down the fixed lid with contributions coming in from low-level convergence, and they also introduced a time scale. And when they did that, and they used a time scale of about 30 minutes or so, so the left side is the simulation, and the right side is the observed values of zonal, meridional, and the divergence. And they see that, okay, they're able to replicate what is happening in reality with this model. Okay. And there's many other variants of linear Ekman balance models. And the one that I wanted to point out is the mixed layer model, where they also account for vertical mixing through entrainment. And this was first proposed in Stevens et al. In 2002, and it was also extensively verified in Rajat paper. And that's one of the figures from this paper is shown here. So you have what the low-level convergence given by this model, and the low-level convergence from reanalysis. And you see that, sure, the model kind of exaggerates the values in some parts of the ocean basin, but on an average, it captures the patterns fairly well. You can already see that there are some contradicting models coming up, right? So there are some models which say that advection is important, and some which do a fairly good job of capturing the winds without advection. So the last study that I want to talk about in this section is the study by Gonzalez and Schubert, where they solve the equations given here on a sphere. And they try to look at like what are the relative importance of the different terms. So how important is advection with regards to Coriolis, with regards to friction. And there's a lot going on here, but the color that I want you to focus on is the black curve. And look at the second panel, which shows the tendencies in the meridional momentum equation. And you see that near the equator already, when you south of equator, it's fairly close to zero, and the dominant balance is between, let's say, friction and the sum of Coriolis and pressure gradient. But as you cross the equator, you have the advection term kind of becoming more and more important. And this region is where their ITCC is. And you see that within the ITCC, there's a very strong role that is played by the advection. And this is what they call that violation of Ekman balance in East Pacific ITCC boundary layer. And they say that if you want to capture this, they ran this model on a bunch of different resolutions, so from coarse to fine. And you see that the magnitude of this term kind of increases as you go to more and more fine resolution simulations. And they suggest that probably the reason why we are missing out is we don't have enough resolution to capture the nonlinear terms. Okay, Okay, so like I mentioned already, there's like different pictures emerging. The nonlinearity seems to be important in some models and not important in others. So my question to you is, can we discuss a little bit about why do you think this is happening, or which model you think is right, or you think all are right, but we miss a perspective to like put everything in context? There are no wrong answers. I'm just curious to hear. Yeah, then why is advection important in one versus not in another?
Is it? Yeah. So, like we are talking about plus minus 2, 3, 5 degrees of about the equator, right? We're seeing like initially when you saw the geostrophic balance, the pressure gradient and Coriolis. And typically we would read Coriolis, we would ignore at the equator. So how do we reconcile this with this in the model?
Sorry, can you repeat it again? I couldn't hear you fully.
Oh, okay. So like in your model, we have Coriolis force, right? And we are in the equatorial region. So how do we reconcile this with the perception that we typically ignore Coriolis force?
Right. So you're absolutely right. Coriolis force near the equator is close to zero. So it depends on the flow. So if you have like a flow where, let's say, the as near the equator, the pressure gradients are kind of close to zero, then I guess friction can do the job, and there's convergence and frictional convergence, and it should be okay. But if there's a cross-equatorial flow, then you definitely have an imbalance, because there's pressure gradient trying to force a cross-equatorial flow, and you would need Coriolis not doing its job enough because it's not strong enough, and you have friction. So there's a little bit of like the imbalance that comes in, and that's where the advection comes about. Did I answer your question? Okay. Yeah.
Consider the upwelling. Yeah. Just want to say that the cross-equatorial flow, basically the winds are response of the heating, right, in general. So if your cross-equatorial flow is getting intensified along the coastal or wants to cross the equator, does the upwelling plays any role on in the equator or in the open ocean upwelling? You haven't considered anything, or you haven't mentioned about the upwelling of whether it is helping or suppressing the winds speed?
Yeah, so I think that's the idea with the Linson and Needham type model. So you have the upwelling, which kind of reduces the sea surface temperatures near the equator or near the coast. It plays a role in setting the pressure gradients that you have in the atmosphere. So it's inherent in the model.
This is kind of a whimsical comment, I would say. But what if we apply these models to extratropics and higher latitudes to see which parameterization of the pressure gradient works best there? Because you don't have the issue with the Coriolis, and then you can apply that to the equator. It's very whimsical.
Yeah, I think probably I don't want to say this, but I think the interesting things happen near the equator because the Coriolis kind of goes away, and you have like this region where sort of the flow is not it's not in a rotating frame of reference in some ways. And I think Vishal and Rajat kind of call it like the critical order latitudes, right? So I think it's a good point, but the interesting things within the advective boundary layers are happening because there's no Coriolis. So you need maybe like a beta plane to still have to capture the change in the Coriolis that happens very dramatically at the equator because the derivative in Coriolis is the highest. Yeah.
I think we can push this discussion to the end of the talk. I just derailed by mentioning Coriolis, I guess. We can get on with this question that which theoretical model do you think is better for in the context of what Divya was saying?
Okay. So my answer would be, it depends. So I think I want to take a look at like the ITCZ in the Eastern Pacific and Atlantic during boreal summer, where we know there's one of the strongest cross-equatorial flows. And if there's an advective boundary layer, you would have to find it there. And let's look at what is happening there. So we've already looked at the meridional migration in the first few slides of the different patterns. And so this is again the work of the authors who put together the meridional migration of the different characteristics. And this is summarizing what the surface distribution of like the winds is like. So you have the streamlines in the zonal meridional direction. So you have southeasterlies moving north, and they cross equator, so which is given here by 0. And as they cross equator, they kind of turn more and more clockwise. And right about the point where they turn clockwise, you have this like dotted region starting, which is the region of low-level convergence. So somehow where the winds turn east is where the low-level convergence is located. And as they keep turning, at some point you get a maximum in convergence and precipitation, which is given by this dotted line, I would say. And you have winds coming in from the northeast. And again, there's low-level convergence as they come towards the ITCZ, and the two trade winds meet here. So similar to what we saw, the maximum precipitation and convergence are located in the southerly regime. And the other really remarkable feature of this time of the year is how broad the low-level convergence is. So it's about 7 degrees broad, and that's fairly wide ITCZ, I would say. Okay. And these are observations from 50 years ago. And I also want to show that, okay, I'm not working on a problem that is 50 years old, but these, these are observations in the East Pacific in a campaign, I think that was done in the late probably towards the end of the 2010s. And you see, again, also in the East Pacific, you have the meridional flow given by the arrows here. And you'd see that all of the convection that is happening in the cross-equatorial flow. So you have the southerly flow crossing the equator. And they also observe what is known as edge intensification, which is also brought together in this paper. But you see both the peaks are located within the cross-equatorial flow. And we still they don't include where the northerlies are in this schematic. And similarly, this is another field campaign that happened in the Atlantic ITCZ. You have a similar picture emerging. So you have the cross-equatorial flow, and the dominant precipitation is located in the southerly regime. You have some precipitation also in the northerly regime, but the dominant precipitation is in the southerly regime. And you also see that, so the cross indicates easterly zonal wind, and the dots indicate westerly zonal wind. And you see that precipitation is also co-located with the westerly zonal wind. And that is also shown in this plot. So you have, as the flow turns, you have the onset of low-level convergence. Yeah.
Does the zero point of the wind, I mean intertropical front, if you like, does it coincide with the northern edge of precipitation minus evaporation greater than zero or something like that?
I'm not sure about the moisture budget, if it coincides with the P minus E.
Yeah, in some sense here, the northerly flow is seen to come all the way until the northern edge of.
Yeah.
I mean, in some sense, in other words, I'm asking, do we have to just model the confluence or just the deceleration of winds?
I would say deceleration of winds, but what is driving the deceleration is the question. Yeah, so is it like a dynamic, something that comes out because the nature of force balances is different, or it's something that's coming out of frictional convergence?
Sure, because in the African monsoon, I think context, this question has been highlighted a little bit, I think, that the intertropical front is somewhere else, much norther, at much higher latitudes.
Yeah.
And then the distance between this front and where the precipitation is keeps becoming lesser and lesser as the season progresses.
Yeah, but I think it's a little bit different. If I remember it correctly, what they see is that low-level convergence and precipitation are displaced. And that's not what is happening here. Here, the low-level convergence and precipitation are sort of acting together. Yeah, I think that's the difference. And that's why they don't call it the Intertropical Convergence Zone, but like tropical rain band is what I vaguely recollect.
Maybe Michaela knows the literature much better. I guess they call it intertropical discontinuity or something of that sort.
In the Africa context?
In the African. Right. I see. Sure. Yeah. Thanks.
Yeah, okay. The way that I worked on this problem is I take a look at the global kilometer scale icon simulations that were done. And I look at the two regions, like the East Pacific and the Atlantic, indicated by this, the black boxes. And I see what is happening in terms of the force balances and try to understand the dynamical structure. And before I go into the details, I thought I would play this animation and point out a few things that I thought when I first saw it was cool. You could see the diurnal cycle in the precipitation. There are some features that this model, this is not the model that the run that I end up using in my analysis, but you could see that there's like a deficit in the precipitation in the West Pacific. And you would see like a lot of tropical cyclogenesis kind of happening in the East Pacific. And you have the easterly waves coming in through Africa. Yeah. Yeah, there's in this version of the run, the model, there's lots of tropical cyclogenesis that happen in the East Pacific. Okay. There's 5 years of model data, 5 kilometer global data. I focus only on boreal summer and I composite over the 5 years of June, July, August. And the first thing that I wanted to check was, do we see that there is the precipitation is dominant in the cross-equatorial flow, or is it equally distributed between the two trade wind regimes? And for that, I plotted the precipitation monthly mean here. And I also plotted the contour line of zero meridional wind, which is the confluence or where the trade winds meet. And you see that in both East Pacific, so I look in 125 west to 105, and in the Atlantic, the precipitation is in the southerly regime. And this is another animation of the total water vapor in a column. And you'd see that, because it's a tracer, you'd see the features of the flow. You have flow coming in across the equator and it turns to the east, and you have the highest values of the humidity located there. And you also have the easterly waves coming in, so there's a lot happening there, but you do see the features that we saw from the work from the 70s. Okay, what I want to show you is first the meridional momentum budget. So I took the equations that I put in my first slide, and I made some assumptions. So I assumed steady state, and I zonally averaged, and I neglected vertical transport. And the equations reduced to this form. And I look at the relative importance of all of the terms. And that's shown here. So the y-axis is each of the terms, and the x-axis is latitude. And the ITCC in East Pacific is located, given by this orange dash, and the Atlantic ITCC is given by the blue dash. And if you want to understand if this is important, if the advection is important or not, we just look at the dashed line, and you see that it's comparable in magnitude to Coriolis, which is the dashed dot line in both basins. And if you are away from the equator, you see that there's geostrophic balance kind of playing a role. So you have pressure gradients balanced nicely by Coriolis in both basins. And as the flow crosses the equator, you have the advection term becoming important. And the advection term kind of changes signs when the Coriolis also changes signs, which is the onset of westerly winds. So it's consistent with what we've been seeing through observations, and also, and we also see that advection is important. The next analysis that I want to show you is the zonal momentum budget. And one way, so I started again with the zonal momentum equations and assumed steady state and did zonal averaging. And this is the set of equations that I end up with. And zonal momentum budget can also be understood by looking at vorticity, because this is the negative of vorticity. So if you have relative vorticity that is comparable in magnitude to the Coriolis parameter, then you have advection being important. And that's what is shown. So these are composites, unlike the previous ones that I showed, which are just zonal means. So this is absolute vorticity in the y-axis as a function of latitude. This is low-level convergence as a function of latitude. And this is relative vorticity as a function of latitude. And you would see that, so the dashed dot line is the F for the two basins. So East Pacific is orange and Atlantic is blue. You see that whenever there is a cross-equatorial flow, so these are the equators. So again, orange is East Pacific and blue is Atlantic. You see that whenever there's cross-equatorial flow, there's a really strong influence coming in from the relative vorticity. And inside of the ITCC also you have a very strong vorticity because of the stretching that happens due to low-level convergence, and it stretches the vortex. And yeah, so throughout you'd see that the relative vorticity is comparable in magnitude to the Coriolis parameter. And this shows that even in zonal momentum, advection terms are important. So I also wanted to, I didn't have this slide, but I added it in last night because it might give you the impression that, okay, the linear balance models are probably wrong because advection is important. But I want you to look at like the sea surface temperature, which is given in this plot, and compare it with the surface pressure. And you would see that a lot of the effect of sea surface temperature can be seen on surface pressure. So near the equator, which is given by the colored labels again, you have like a local dip in SST because of the upwelling, like we were talking about. And that manifests in the pressure as a higher like pressure. And the pressure trough is not like a simple parabola that you would see. So you would see the effect of upwelling coming into the pressure profiles. And near the ITCC, where you have higher sea surface temperatures, you see like a local minimum. And of course, there's coupling because there's also effects of convection, which reduce the pressure, adjust the pressure a little bit. So the Linson and Negam type thinking also fits in with what we observe. And here I have zonal and meridional winds because we saw that from the observational paper in the 50s that wherever we saw the starting of the dotted region is coincident with the low-level convergence or the onset of westerly wind, sorry. I wanted to see if the onset of westerly wind is kind of co-located with the maximum in the meridional wind speed. So this is the zonal wind speed and the meridional wind speed. And I kind of plotted two like markers here in gray to point out where the wind turns westerly. And you'd see that it is actually close enough to the maximum in meridional wind speed. And beyond that, you would get convergence. So it kind of goes back to the paper the first advective boundary layer study that we saw, where the paper was suggesting that when the flow transitions from an advective to an Ekman sort of a boundary layer, you get upward motion. And you see something similar happening in this simulation as well. Okay, so I think this is probably the last slide. So then I looked at like convergence as a function of height and latitude in East Pacific and Atlantic, and you see the upward motion on the meridional circulation through the streamlines here. The red indicates low-level convergence, and the green contours are the onset of westerly winds. So you see that sort of the westerly wind onset is nicely encompassing this region of low-level convergence. Of course, it works better in the East Pacific and Atlantic, and there's some differences that depend on the sea surface temperature distribution. But yeah, that summarizes my talk. So we saw that there's east-west asymmetries in the ITCZ, and we cannot really ignore them if we want to understand what is happening locally. And in the Eastern Ocean basins, there's a maximum located typically in the cross-equatorial flow. And idealized studies and icon simulations have shown that within this cross-equatorial flow, advection is not negligible and Ekman balance is violated. And we also saw that the onset of westerly winds is actually a good indicator for low-level convergence. Thank you for your attention. Happy to take questions.
We have questions. Okay, I'll just give him the mic first. Let's usually ask one question during the talk.
I had a naive question. Like usually in incompressible flows, pressure is a dependent quantity constrained by the incompressibility with the Poisson equation. So what's the motivation or justification of prescribing a pressure independently and then looking at the flow?
Yeah, that's a great point. I think it's in atmospheric flows, you also think of pressure as like the weight of the atmospheric column. So yeah, I think the pressure Poisson is probably not a good way of like looking at it. And that's why, because it's the weight of the atmospheric column, you have the influence coming in the way that it does, I think.
Also, prescribing pressure and solving for the velocity, wouldn't it only work for linear balance equations? Like once you put nonlinear balances, would it work out prescribing pressure and solving for the velocity?
Yeah, so that's what the idealized study in the 70s, the first one that I showed did. So it's this one. So they solved these equations. They had, but they prescribed the pressure gradients. Yeah.
Thank you.
Hello. Hi. I'm interested in that 5-kilometer simulation that you have shown. The 5-kilometer simulation that you have shown. Are you entering the gray zone because at 5 kilometer it is neither parameterized or nor resolved, right? So don't you think that 5-kilometer simulations is overly predicting the updrafts or some kind of an issue will be there if you go for the kilometer scale modeling?
Yeah, so there's no convective parameterization in this version. Yeah, but I think 5 kilometers still is okay. There's popcorn convection that a lot of these high resolution models suffer from. Yeah, but I think for for this type of questions where you want to understand the link between like boundary layer convergence and the clouds and precipitation, I think it should be okay because you're not looking on smaller scales. But
No,
I guess
because
it depends.
Because why I'm asking is that the 5 kilometer is assumed it has to predict the updrafts and downdrafts, because since you don't have any convective parameterization, the model itself has to predict the updrafts and downdrafts.
Yeah.
So I was just speculating. I don't know, because we are planning to do the 5 kilometer simulation as well.
I'm curious to hear more about that. Yeah.
Thank you.
I guess, hello? Okay. So how long was your icon simulation? Month or something?
No, this was 5 years.
Oh, it's 5 years. Okay. Well, yeah, so that's good. So my question was, the MJO, boreal summer manifestation actually causes really big changes to the basic state in this region where the ITCZ is either pushed pretty far south or pretty far north. Have you considered looking at some of the intraseasonal variability in the force balance to see if that verifies some of your thinking?
Yeah, that's actually a really good point. I don't know if this would answer this question. So I did look at like the composites for different years, and I looked at like how much they vary, and they don't vary by that much. But we also, I don't think we have an MJO in this version of the run, so possibly, yeah.
Maybe you can do composite kind of thing instead. Just
Yeah.
I think like the push far south, very far north.
Yeah, I'm actually curious to hear more about it from you. Maybe we can discuss it later. Yeah.
Hi. So since I didn't see you looking at the land surface, like you're specific on the oceans. So I was a bit curious about the Indian monsoon situation. So usually what happens is we have this monsoon trough, and most of the organized precipitation, even on the Indian region, is over the cross-equatorial edge.
Yeah.
It is not much on the other side where we have the other side winds. So it's always on the westerlies that the maximum precipitation is situated. So can we think about a situation like this, like where what is making this asymmetry in the Indian monsoon region as well from this kind of a framework?
Yeah, I think that's a really good question. Indian summer monsoon also has the zonal pressure gradients, right? And so far in my thinking, I haven't like developed an intuition for what a zonal pressure gradient would do to this picture. But it would be interesting to like look at it. I think Harshit coded up this model, the 1972 model, and there you can also prescribe the zonal pressure gradient, and it would be good to play around with it and sort of develop an intuition for what is going on when there's zonal pressure gradients. Yeah.
Just to add, just to supplement your point to Gokul, the picture would be entirely different for the Indian monsoon region. That you have showed the convergence zones and the precipitation rainfall band. They are co-located kind of a thing. In the eastern or western Pacific, you have showed a theoretical diagram. So that convergence zone would be very different when you go the same picture if you draw or the Indian monsoon or the Arabian sector where the cross-sectoral flow is much faster.
Mm-hmm. Yeah. Thank you. Yeah.
I guess I had a related question or comment that, like, how would you like to edit or modify your model for Western Pacific? Because there, the dotted zone that you showed of 7 degrees would be like in monsoon zone or Western Pacific, there will be many more degrees.
Yeah, that's a really good point. I actually keep thinking about it. Maybe like this type of a thinking wouldn't work for that, because you also have precipitation near the equator, and the trade winds kind of meet close to the equator. So this thinking wouldn't work. But I would say like it's a good way to kind of diagnose the double ITCC biases, because if you have precipitation, the model is not precipitating near the equator, let's say, then from this framework you can explain it in some ways because you have the divergence coming in and yeah.
Two more questions, I guess. Yeah.
Hello, yeah. Hi, Divya, really nice talk. So I wanted to ask, like, should there be a buoyancy term in the vertical velocity equation? Is it important because near the equator, when there is no cold system, usually the buoyancy terms is pretty significant because it picks up the plumes. Do you think we should also add some kind of buoyancy term, or is there any model like that?
I probably am not the right person to answer if there's a model that includes the buoyancy term. So far, I've only like kind of looked at like the simple dynamical models. Maybe someone like Jim would know better. Yeah.
Can I ask? Thank you. Thank you for nice talk. And I have a question about the meridional momentum budget you showed. And I noticed that there is, in this figure, the surface friction terms have very large spread. What caused this spread, and that it comes from boundary layer depths or something?
Yeah, so one of the model outputs that we have is the surface stress integrated over the boundary layer. So I had to go from that to kind of like from an integrated value to a value at a point. So I assumed like a boundary layer height between 500 and 1500 meters, and that's the spread that you get.
Do you have any direct diagnostic of boundary layer depths? No, you have no.
Yeah, so the other thing that I did, which is shown in gray, is basically compute the friction as a residual. So the gray solid line is supposed to be compared to this spread. And you see that it's not perfect, but it's okay, yeah.
Okay,
Yeah.
Thanks.
Yeah, I guess we can wrap up the session before lunch. So let's thank Divya again and all other speakers. Yes, it's only Divya who can hear us clapping. All others are online.